Good morning all. We will start our session now.
Yes, sir.
Yeah, and I will just introduce the speaker of today, Dr. Balachandran Rao. I actually am honored that Dr. Balachandran Rao has come and he has agreed to speak in this FDP in spite of his ill health and in spite of his having a busy schedule. The thing is that from our younger days, actually, he has written so many books, and we have developed our a lot of galleries studying his books. And I still remember that when we were developing our astronomy gallery in our center, and his book on Indian astronomy, and where he has actually written in details the various instruments which Aryabhata has made. He has described that, and reading that we tried to recreate those some of the artifacts and we have placed it in our center. So thank you, sir, for all those great descriptions which you have given, which has helped us. But formally I will just introduce Dr. Balachandran Rao. Now, he had been teaching initially, and after that he has been teaching for 15 years, and after that he was the principal of National College, Bangalore, serving the institution for 35 and half years teaching mathematics. And he has also been the director in Bhavan's Gandhi Center of Science and Human Values. And currently he is the member of International Astronomical Union and honorary fellow of NIAS Bangalore. He has authored more than 35 books in English and Kannada related to classical Indian mathematics and astronomy. And he is still active in writing and researching on ancient Indian astronomy, and we will be hearing Professor today. So, Professor, with this brief introduction, I request you to kindly deliver your talk.
Okay. Thank you very much. Dear friends, a very happy good morning to all of you. I am thankful to Professor Ganguly for introducing me with kind words. And today, in my today's talk, I shall try to present some glimpses of the development of astronomy in India, right from the Vedic times up to the famous Kerala School of Mathematics and Astronomy. Of course, Ramanujan is not included because, formally speaking, he does not belong to ancient and medieval Indian heritage of our astronomy. And of course, he didn't do anything in astronomy. He is basically a pure mathematician, and he belongs to the modern group of mathematicians. Therefore, he is not included in this list. So, up to Kerala School of Mathematics and Samanta Chandrasekhara Simha of Odisha. He is the last barefoot astronomer belonging to the traditional group, and I will try my best to go up to that, but I don't know how far I can do justice to the subject. So I will commence with the next slide. Anyway, I will be keeping on talking until you see the slides oblige us. Our available record, the literary record of the development of our Indian astronomy starts with, strictly speaking, Vedanga Jyotisha. Even before Vedanga Jyotisha, in the Veda Samhitas, like Rig Veda, Yajurveda, etc., references are there of astronomy.
Sir, your slide has gone. Your slide, yeah, okay.
Yeah.
Okay.
There is some problem.
Yeah, okay. It has come.
It has come. The next slide I am supposed to show. Yeah. I'll start with this oft-quoted shloka from the Vedanga Jyotisha. Vedanga Jyotisha is the earliest available text on astronomy written in Sanskrit, and there it is purely an astronomical text. I will come back to that a bit later. I am quoting a famous shloka from that, which tells you the importance of astronomy in the Indian knowledge system. It says, for those who love Sanskrit, I will quote from Sanskrit, Yathashika Mayuranam Naganam Manayo Yatha Tadvad Vedanga Shastranam Jyotisham Murdhanistitam. While typing the Devanagari script, there are a few mistakes here. Well, it was not done by me. It was done by an old student who was not familiar with Sanskrit or Devanagari script. So kindly pardon me for such typos. What the shloka says is, Yatashika Mayurana. We know that our national bird, which we love most, is the peacock. And on the head of the peacock, there is a tuft of hair, which adds to the grandeur of the Mayura or the peacock. Similarly, it is a poetic imagery in Sanskrit as well as in other Indian literature that Naganam Manayoyata, the Nagas or the cobras are supposed to have a mani, gem, hidden in its hood perhaps. Physically, we know that no such thing exists, but it was an interesting poetic imagery generally used in Sanskrit literature as well as our other Indian literature, that the mani or the gem adds to the beauty of the cobra. Tadvad, like that, Vedanga Shastranam, among the auxiliary sciences of Vedic literature, 6 such Shastras are given. Among them, Jyotisha also is there. Jyotisham Murdhanishtitam. This Jyotisha or astronomy is at the top. It is the foremost important branch of auxiliary Shastras to understand the Vedic literature. Here, just a word or two on the meaning of the word Jyotisha. Jyotisha in modern parlance is used to mean predictive astrology based on horoscope, whatever prediction is being given by astrologers. Unfortunately, that goes by the name of Jyotisha in modern times. But please note that in ancient and medieval Indian literature, the word Jyotisha meant exclusively planetary and calendrical astronomy, not astrology. So predictive astrology doesn't find a place in Vedanga Jyotisha or for that matter, even in the earlier Vedic literature. I can confidently tell you that Vedic astrology is a misnomer. There is no such thing as Vedic astrology at all. I mean, I leave it to you to think more about it. I will further proceed to discuss about the planetary and calendrical astronomy as developed in Vedanga Jyotisha and later Siddhantic period started with Aryabhata. Well, the next sloka tells you that in those times, during the Vedic period, this astronomy was used mainly for fixing timings, the appropriate times for the performance of yajnas and yagas, because that was the main preoccupation of the priestly class of the Vedic times. So, in a way, this religious preoccupation of the ancients was greatly responsible for the development of astronomy, even mathematics for that matter. The earliest text available to us are the Shula Sutras. Shula Sutras comprise geometrical results and constructions for constructing the sacrificial altars or the yajna bhumikas for the purpose of yajnas and yagas. But considering the fact that all this literature developed around, I don't know, at least 3,000 or 4,000 years back, it is really remarkable that a contemporary development in other ancient cultures cannot be seen like that. It was a really sophisticated development of mathematical and astronomical literature that developed during the some Vedic period and the post-Vedic period. Okay, the next slide. In the presentation that I am going to make, some random references I do make. So I am not strictly chronological in presenting these things before you. Now I am quoting from the famous Kerala astronomer And really I envy my Kerala friends because unfortunately I'm not born in Kerala, but I have great love for Kerala and its contribution. At least for two reasons, I love Kerala's contribution. Firstly, in the field of philosophy, it was Kerala which gave us Adi Shankaracharya, the propounder of the Advaita Vedanta. And coming to mathematics and astronomy, the most remarkable contribution has been from Kerala. And I will come to that point later. Now I am quoting one of the topmost Kerala astronomers, K. Nilakanta Somayaji. He lived around 1500 CE, and his Tantra Sangraha is the magnum opus, in which also he has composed other texts like so many of them. In one of them, he pays rich tributes to his Paramaguru, grand teacher, Guru's Guru, Parameshwara Acharya. He says, my great teacher, grand teacher, Parameshwara, did like penance observations of astronomical phenomena for 55 long years, and having done that, he critically examined mathematically his observations and composed the famous text Samadrugganitam. So he says, Pancha Panchashat Varsha Kalam, that is 55 years long, Niriksha, having observed. What did he observe? Grahana Graha Yoga Adishu, eclipses and planetary conjunctions. When we say planetary conjunctions, we include transits and occultations of stars and planets, mainly by the moon, which we call lunar occultation. Today you are going to listen to a very brilliant talk on occultations and transits. Of course, transit of Mercury and Venus, they could not observe because no telescope was, reflective telescope was not available. And further, with the naked eye, you couldn't observe a Venus or Mercury transit. Yesterday we had a very brilliant talk by Professor Mahesh Shetty on calculation of eclipses, occultations and transits. Today I am not going into details of calculations. My presentation will be more of a general nature. However, that will be followed by two of my colleagues who will be going deeper into the subject. And the shloka of Nilakanta says, Pariksha, having examined the observations that Parameshwara made, he composed the famous text Samadrugganitam Karanam Chakara. Samadrugganitam, what is that? Drugganitam, Druk plus Ganitam. Druk means observation and Ganitam means computation. Samadrugganitam, they must be concurring with each other. There should be concordance between observation and computation. That was the hallmark of all Indian astronomers, even starting with the Siddhantic period and even before the Kerala school. Every astronomer insisted that the parameters must be revised, must be updated frequently based on observations. For example, Vasishta Siddhanta, one of the Pancha Siddhantikas given to us by Varahamira, that Vasishta Siddhanta insists that Tithi, Nakshatra, etc. should be decided based on observation. Only that system must be adopted because various other systems may be there, but that which gives you concordance with observation should be accepted, and accordingly you must have your rites and rituals performed and so forth. So Karanam Chakara, what is this Karanam? Karanam in this context means a handbook, a manual. Just as in our physics, chemistry, etc., we have the manuals or the handbook for ready performing of experiments. Here also they are basically algorithmic. These Karanas are short handbooks and they are not treatises like Surya Siddhanta. And these are algorithmic in the sense, right, straight away you can make calculations. And today in this age of computer science, we can transform those algorithms into programs in any suitable language. And we here in Bangalore are a team who have been doing that sort of work. We are computerizing the algorithms given in these handbooks starting almost from Brahmagupta period, and it is interesting and exciting to compare our Indian results with those of Ptolemy's Almagest and Copernicus De Revolutionibus, and how good the Indian computations are. I am indeed proud to tell you that our Indian computations are reasonably accurate, and even eclipse prediction comes true. And in spite of telescope being not available then, in spite of having no Kepler or Newton in India, it is very remarkable that these people here, the great stalwarts of the ancient and medieval period, purely based on observations and their brain was perhaps too active, so they could contribute to so much to it. And like that, Parameshwara is highly praised by Nilakanta. Again, Parameshwara says, whatever I have given in my text, he has written small handbooks on computation of eclipses and other phenomena, but he is not satisfied. He says, Kalantaretu samskara chintyatam ganakottamai. That means, in course of time, Kalantaretu samskara, that means correction, chintyatam ganakottamai, must be thought over, must be implemented by whom? By the best among mathematicians, ganakottamai. That's what he says. Now going back to our Vedic literature, in Rigveda, Yajurveda, etc., you see some concrete references to some astronomical and calendrical phenomena, like the seasons, the 6 ritus, then the definition of the year. Those of you who have listened to these earlier lectures are familiar with the different types of year: tropical year, solar year, sidereal year, and anomalistic year. Yesterday, Professor Mahesh Shetty made a reference to these things, synodic month and things like that. So you do see references to some of these things in our Vedic literature. So also Nakshatras. One of the major contributions of ancient Indian astronomers is the concept of Nakshatras. The zodiac is divided into 27 Nakshatras, with which you are all familiar, Ashwini, Bharani, etc. And in our computations, each nakshatra is of angular range 13 degrees 20 minutes. That is 13 degrees 1/3. How do we get that? By dividing 360 degrees of the zodiac by 27. That is the angular range of each nakshatra. But actually these nakshatras are named after what are called the some fixed stars like Ashwini, etc. They are called Yogataras, that is individual stars, and they are not placed with equal distance. Though the angular range of today's nakshatras are 13 degrees, 20 minutes, etc. But the angular distance between the Yogatara or the fixed star Ashwini and its next one Bharani is not 13 degrees, 20 minutes. Sometimes it could be just 6 degrees, sometimes it could be nearly 20 degrees, like that. So they actually started with those fixed stars to locate the motion of the moon. But in course of time, for mathematical convenience, they made them of equal angular range, as I mentioned. But note that there is no reference to Rashis, Mesha, Vrishabha, etc. today, which we have. There is no reference to Rashis in our Vedic literature. And like that, they were very aware of equinoxes, the vernal equinox and the autumnal equinox. You see that the sun comes to vernal equinox around March 21st and to the other equinox, autumnal equinox, around September 23rd. And most of you will be knowing why they are called equinoxes. On those 2 days, the world over, the duration of the day and the night will be equal. On other days, for us in the northern hemisphere, day will be longer during 6 months and it will be shorter during the other 6 months. It will be longest on June 22nd when the sun will have reached the summer solstice, And when the sun reaches the winter solstice around December 22nd, the day will be shortest and the night will be longest. For those in the southern hemisphere, it will be the other way. So these things are known to our modern students, even at the high school level. But what is significant is, in the Vedic literature, which is more than about 5,000 or 6,000 years ago, such references are concretely given, and for them those phenomena were very important for their yajna and day-to-day religious and social activities. And equinoxes also they do refer, they call them Vishuvas. And Nakshatras, in the Rig Veda, for example, you don't have the list of all 27 Nakshatras. Not that they did not know it. They were definitely aware of the 27 Nakshatras, but only some of them they have mentioned, like Maga, then Tishya and so forth. That is because those were considered as important Nakshatras for performing certain particular rites and rituals. For example, one mantra in the Rig Veda says that the dowry of cows given by Savita, the sun god, had already gone ahead of his daughter Surya. That means his daughter Surya, Akaranta Strilinga, for those who love Sanskrit. So she was married away, and the father's sun god sent the dowry in the form of cows already before daughter Surya left for her husband's place. They drive the cows on the Aga Nakshatra. The mantra tells on which date the cows were sent on the Aga Nakshatra. Aga is
3-4 questions there, just to write the question. कौन सा question था बोल दो? 11 है ना के 12?
Yeah, tell me.
11 था ना? Right, question number 11.
Shall I continue?
Number 11 question लिखो.
और माताड़ती रहे. Okay, some interference of talking is there from the center or elsewhere. It doesn't matter. So on Maga Nakshatra, the cows were sent away to daughter's place. The daughter, that is bride, was carried away, that was to her husband's house on the Arjuni or Palguni Nakshatra. Today we have Uttara Palguni, Dakshina Palguni, like that. So on the Arjuni star, that is Palguni Nakshatra, the daughter was sent. Prior to that, in the Maga Nakshatra, now coming to the list of 27 nakshatras, we find them in Taittiriya Samhita, that is in the Yajurveda. In the Yajurveda and later Atharvana Veda also, you will see the list of 27 nakshatras. But sometimes 28 nakshatras are mentioned. The 28th one is Abhijit. Abhijit Nakshatra is there. For some reason, I don't go into the detail. There are many stories connected with these nakshatras, and some have astronomical significance. All that is not mythology. Some of them have astronomical references. In fact, some great scholars have worked on the astronomical significance of the stories behind these nakshatras. Well, not because of the time does not permit us to go into details. So, I was referring to Abhijit Nakshatra. That in due course, they dropped out that Abhijit Nakshatra somewhere near Shravana, that Abhijit was seen. And it is interesting, though it is not immediately close to the reference. So, Abhijit Nakshatra and Agastya. These two have some historical significance astronomically. Abhijit Nakshatra almost became the north polar star, and during more or less the same time, the other one, Agastya Nakshatra, which is a southern star, became almost a southern polar star. They were not exactly polar stars, because if one star has to become polar, it has to have a declination of 90 degrees. So it may not reach up to that, but anywhere between 85 and 90, often it is regarded as a potential polar star. Like that, Abhijit became the north polar star, and the other one, Agastya, became the southern polar star. But when it is estimated mathematically that it was around 12,000 BC, and our good friend Professor Mahesh Shetty will kindly do well to go into the calculations to check whether I am correct or a better period can be estimated for these two stars to become almost polar stars. So anyway, Abhijit was dropped out. So today we have only 27 nakshatras available to us. Then coming to planets, in the Vedic literature, when I say Vedic literature, I specifically refer to the Veda Samhitas, namely Rigveda, Yajurveda, and mainly Atharvana Veda. So, are there references to planets? Please note that there is a reference, or there are references only to two planets, Jupiter and Venus, apart from the Sun and the Moon. Your Mars, Saturn, etc. are not explicitly mentioned anywhere. Now, the reference to Jupiter or Brihaspati occurs both in the Rigveda and Atharvana Veda, and in Yajurveda also, in a Taittiriya Brahmana. For example, Rigveda tells you that Brihaspati pratamam jayamano maho jyotishaha parame vyoman. And in Taittiriya Brahmana, more specific reference is given of the conjunction of Jupiter with the star Delta Cancri. Delta Cancri is called Tishya in Vedic literature, which is now called Pushya. So Jupiter was in conjunction with Pushya Nakshatra. It says, Brihaspati pratamam jayamano Tishyam Nakshatram abhisambabhuva. That means Jupiter stood exactly in front of Tishya or Pushya Nakshatra. Now, for mathematical astronomy lovers, the question comes, when did it occur? When was Jupiter in conjunction with Tishya Nakshatra or Delta Cancri? By our calculations, it is found that it could have happened around the 4th millennium BC, that is around 4000 BC. Professor S.D. Sharma, one of the reputed contributors to History of Indian Astronomy, produced a paper earlier working out the details. And you may ask, what is great about it? There can be conjunction of a star with a planet periodically. But my friends, this sort of occurrence repeats only after several thousands of years. And close conjunction is virtually very rare. And it is really creditable that as early as the period of Taittiriya Brahmana, such a reference is made that only speaks of the sense of great observation and perhaps the computational techniques those ancient astronomers must have had. So anyway, such references now and then we do find in Veda Samhitas proper. Coming to Venus, there is a reference to planet Venus. You may ask, why are they so particular in referring only to Jupiter and Venus? The reason is obvious. Jupiter is the biggest planet in the solar system, and Venus is the brightest planet. So those two were easily visible to them, and it was considered auspicious to perform ceremonies like marriage, Upanayanam, etc., when either Jupiter or Venus is visible in the sky. So what they call Guru Bala, Shukra Bala, etc. Now, of course, it may have astrological significance, but astronomically speaking, they considered it auspicious to have their religious rites during the periods when Venus or Jupiter is visible. And if both of them are visible, maybe they consider it as a blessing for performance of similar such beliefs here and there. We do see, for example, in Rigveda, Stotaram Vipraha Sudinatve Ahnam Ya. Vipra, that is, Vipra is not a Brahmini here, it is a reference to Varuna, the god Varuna. Vipra or Varuna established the reactor on an auspicious day. So they considered a few days because of counting of Nakshatras. Please note that the days were reckoned through Nakshatras. Earlier they did not have this Tithi sort of thing, though of course lunar phases were easily visible, but they more or less started with the motion of the moon in the zodiac through the Nakshatras. So some Nakshatras were considered suitable for certain rites and rituals. Similarly, another mantra says in Taittiriya Brahmana, Yam kamayet duhitaram priyasyaditi nishtyatam dadyat priyaiva bhavati. When daughter is to be married away, the suitable day for a daughter's marriage is the Nishtya Nakshatra, that is Swati Nakshatra, when she will be happy with her husband and in-laws. That was a belief they had. Of course, how far all that is true or false, it is left to one's belief. But formal astrology was surely not there in the Vedic period, though here and there some auspicious days were mentioned for certain performance of rites, rituals, including marriage, Upanayana, and things like that. Now I will pass on to the Siddhantic period. The mathematical astronomy developed around the 5th century. Not that it started right with Aryabhata, but even prior to Aryabhata, for some 2 or 3 centuries, Siddhantic or mathematical astronomy must have developed, because Varahamihira does mention the names of some of the ancients like Garga, Parashara, Satyacharya and Yavanacharya. By Yavanacharya they meant perhaps ancient Greek astronomers. Like that, some of those names are mentioned, and so we can understand that even before Aryabhata, for 2 or 3 centuries, the mathematical astronomy of planets or planetary astronomy developed. As I mentioned earlier, in the Vedic literature proper, or in Vedanga Jyotisha, which is ascribed a period of around 1200 BC. So in that also, you have only calendrical astronomy and no reference to the motion of planets. So planetary astronomy developed perhaps some 2 or 3 centuries before Aryabhata. But the systematic development of the subject, both mathematics, pure mathematics and astronomy, can be seen in the famous text Aryabhatiyam by Aryabhata I. There are 2 Aryabhatas. The first Aryabhata is the most famous one. He composed his text in 499 CE and supposedly born in 476, because he mentions that he composed the text when he was 23 years old. And he says that when he composed the text, it was 3600 years of Kali Yuga. So taking all those into consideration, it is believed that he was born in 476 CE and composed the text in 499, that is around 500 CE. And Varahamihira was a junior contemporary of Aryabhata, and he is famous for his text Panchasiddhantika on astronomy and the encyclopedic text Brihad Samhita. Well, I don't go into too many details. Then we had in the 7th century 2 great astronomers, Bhaskara I around 600 and Brahmagupta around the same period. Brahmagupta is more famous. and he is considered as mathematician par excellence in India. Not only India, a good development of algebra can be seen in Brahmagupta's text, but however, the credit of initiating all the systematic development indeed goes to Aryabhata of 500 AD. So, like that, there were many of them. I don't go into all those details. Come down. So, Manjulacharya, I must make some reference to him. The sixth item there in the list, Manjulacharya composed a text called Lagumanasam, that is composed in the year 932 CE. Why Manjula is important for us is Kerala has a bit of consideration for the development of calculus even before the Kerala contributors. For example, Manjulacharya gets the credit of giving us a glimpse of calculus even before formal calculus was invented. In 932, as I mentioned, in his text called Lagumanasam, which is a Karana text or handbook of calculations of planetary positions, eclipses, etc. While calculating the eclipse, he says, instantaneous angular velocity of the moon must be considered. The usual practice was to consider the mean angular motion of the moon, that is about 13 degrees 10 minutes. But this man Manjula points out that you should not consider the average motion of the moon, that won't give you accurate results. He says instantaneous angular velocity, which he called Tatkalika Gati. That Tatkalika Gati must be considered for eclipse calculation. Then only you will have accurate Sparshakala, Mokshakala, etc. But then conceptually it's all right. But mathematically does he proceed further to give? Yes, sir. He does give a result equivalent to differential of sine is cosine. We know that d of sine theta is cos theta, d theta. Using tables, he gives the change to get the, or what we call the finite difference, to calculate the instantaneous angular velocity. That is a remarkable development that took place around 1000 AD, about 7 centuries before calculus was formally invented by Newton or Leibniz. I will come to that point a bit later. So anyway, Manjula gets the credit. Next, similar concept is continued by Bhaskara II in the 12th century. Bhaskara II is the most popular among the Indian mathematicians and astronomers for various reasons. His famous astronomical text is Siddhanta Shiromani. And he also composed a smaller text, a handbook or Karana Grantha called Karana Kutuhalam. I am proud to tell you that we from Bangalore translated Karana Kutuhalam into English, and it is published by Indian National Science Academy, INSA. Anyway, further work is being done on this text by other great scholars also elsewhere. And besides Siddhanta Shiromani and Karana Kutuhalam, Bhaskara wrote 2 pure mathematical texts with which many of you will be familiar. One is the popular Lilavati and the other one is Bijaganitam or algebra. So anyway, Bhaskara II is extremely popular for the text that he composed. Apart from that, he was a very good poet and his language is simply beautiful, very simple and beautiful chandas he uses in his compositions, and that means he was a very good teacher. That you can easily discern from his Lilavati text. Very beautiful examples are set out, and I request our colleagues in mathematics that are listening to us to popularize such a text among the students at various levels. Now, why I refer to Bhaskara II in this context is the calculus concept. He continues with Manjula's concept of instantaneous angular velocity, Tatkalika Gati. But further to that, he gives us a result which is equivalent to telling that at the maximal point, Brahmagupta. At the maximal point, the derivative vanishes. dy by dx equals 0 today we know is a necessary condition for a function to attain maximum or minimum. This very result the second Bhaskara gives in his Siddhanta Shiromani. And in fact, from that, the derivation of the critical points of the motion of a planet, that is a retrograde and direct and all that, the critical point, in fact, what our Indian astronomers have given as critical points, what I mean by critical points is, in regular motion of a planet, you see that it moves eastward. But for some period, it seems to move backwards. That is called Vakragati or retrograde motion. And the point at which the motion gets changed from direct motion to retrograde motion, and then later on from retrograde motion to direct motion, those 2 points in the calculus language are called critical points. And it is really amazing that our Indian astronomers have given the precise critical values when the nature of motion changes. And using modern computations, you can arrive at almost the same result. And please note that calculus was not yet invented before Newton or Leibniz. And of course, there are theories from our scholars as to how calculus must have traveled from India to European shores. Well, I'm not going into the details of the controversy, though I may make a mention here and there of such things. Then the period of Kerala astronomers starts. And as I mentioned, Parameshwara is among the top Kerala astronomers. And before him, that is before 1400 CE, there was the great Madhava. And Madhava, unfortunately, all his compositions are not available to us, but his greatest contribution, not only his greatest contribution of Indian mathematics, is to infinite series. And infinite series of sine function, pi by 6, tan inverse x and things like that, you see in Madhava's compositions. But unfortunately, the original texts are not available, but they are quoted by later astronomers, and you will see further development of infinite series also from what Madhava had done. In Parameshwara's text, we have Drugganitam, commentary of Surya Siddhanta, called Surya Siddhanta Vivaranam, then Bhattadipika, that is commentary on Aryabhatiyam, and many small monographs he wrote on eclipses. But still, as I mentioned earlier, he is not satisfied with his results. He mentions that Kalantaretu Samskaras Chintyatam Ganakottamaihi. And I also quoted his Prashishya, Nilakanta Somayaji, that his Paramaguru had made observations for 55 long years of eclipses and so forth. And in fact, in his Bhattadipika commentary, Parameshwara gives a list of about 15 eclipses which he observed from his place in Kerala. And we verified all of them, and all of them tally very well. And on the dates he gives, and one great practice these Kerala astronomers had was to mention dates through Kali days. That practice was not there elsewhere. In other compositions by other astronomers outside Kerala, we usually see references to Kali year, of course, is given. Otherwise, Vikrama Shaka or Shalivan Shaka year, then the lunar month and so forth. But Kerala astronomers have a unique and almost foolproof practice of giving the dates through Kali days. Even one day error is not there. Sorry. For example, Parameshwara mentions some 15 eclipses which he observed. They were visible from his place on the banks of the Bharatipura river. Personally, I had the occasion of visiting his birthplace when I visited Kerala, and he, more interestingly, he mentions in another shloka the observation he made elsewhere. For example, on a special occasion of a solar eclipse, his calculations revealed that solar eclipse was not visible from his place in Kerala. But then he was curious as a good mathematician as to find the place nearest one where that solar eclipse would be visible. And he found out that it would be visible at Gokarna Kshetra, the sacred place of Gokarna in our Karnataka. And what did he do? He seems to have physically visited Gokarna and made the observation and got the satisfaction that his computation worked out very well. Please understand, those days it was not easy to travel from one place to another, that too crossing so many rivers, sea and all that. And these Orthodox people had their own problems regarding crossing the river or drinking water, food, etc. In spite of all that, Parameshwara seems to have travelled up to Gokarna Kshetra, observed the solar eclipse, got satisfied. These computations were wonderful, and he mentions in a shloka that it was visible in Gokarna, but not in his place. So these are some very remarkable things. And today in our Bangalore team, we have been working on the astronomical tables, sarinis, for Panchanga making throughout India. Sarinis or astronomical tables are used, and there is a variety of astronomical tables, and the Kerala astronomers are famous for their Vakya Paddhati. Vakya Paddhati, if you are not very familiar with it, means sentence. The text gives us some beautiful Sanskrit small sentences. Each sentence has a meaning. The meaning may be not relevant to astronomy, but it is meaningful. And each letter there represents a number. So, for any given date, in terms of Kali days, or Argana as we call it, Kali Argana, you can find the true position of sun, moon and other planets straight away using those sentences. Each letter gives you a certain digit, and the sentence tells you the position of the true position of the planet in degrees, minutes and seconds. It's a wonderful practice which Kerala astronomers had, and even in Tamil Nadu that Vakya system was practiced. But strangely, it never reached the northern part of India at all. So that is incidental. Then Nilakanta Somayaji, whose name I mentioned earlier, maybe he was born around 1465, and in the year 1500 he composed his famous text called Tantra Sangraha. Apart from that, Aryabhata Bhashya, he wrote a commentary on Aryabhatiyam also. Of course, earlier Bhaskara I had composed a commentary on the Aryabhatiyam, but his commentary is not complete. Maybe he passed away or something. So anyway, Nilakanta's commentary on Aryabhatiyam is valued high, and it gives wonderful glimpses. Because I may not have another occasion to mention, here itself I will mention, it is Nilakanta Somayaji who gets the credit of intuiting what can be called quasi-heliocentric model of planetary motion in our solar system. Today, we all will have read that the heliocentric model of planetary motion was given by Copernicus. Yes, Copernicus was great. Personally, I admire him very much, as also Kepler. But a few decades before Copernicus, it is Nilakanta in his Tantra Sangraha who mentions that in the solar system, the planets move around the sun, and the sun himself appears to move around the earth. Of course, he did not perhaps recognize that earth is also one of the planets as Copernicus recognized. But definitely that this family of planets, other planets, move around the sun is a very significant contribution. Not only that, this Nilakanta very humbly gives credit to his Paramaguru, Parameshwaracharya, he mentions that our great Acharya Parameshwara was mentioning this. So that was somewhere in early 15th century. And our friends M.D. Srinivas and others produced a paper in the Current Science Journal speaking out or enunciating Neelakanta's model, and that was brought to light for the benefit of the scholars world over. And then suddenly among Maharashtrian astronomers, just as Kerala School of Astronomy and Mathematics is very great and remarkable contributions they made, almost similar to that, we have the Maharashtrian School of Astronomers and Mathematicians, and Bhaskara himself is recognized by the Maharashtrians as a Maharashtrian astronomer, while we in Karnataka respect Bhaskara Acharya as from Karnataka. The fact may be that he was born in Bijapur district, but then migrated to Maharashtra, which is very close to Bijapur, because of the change in rulership and all that. So seeking patronage, if not Bhaskara, at least his son and grandson, Changadeva, migrated to Maharashtra. Anyway, Bhaskaracharya is highly respected as one of the top astronomers. So Ganesha Daivajna was another Maharashtrian astronomer who composed the famous text Grahalagavam. Grahalagavam is used as a text even today to teach astronomy and for Panchanga making. What is the greatness of this Ganesha Daivajna? In his Grahalagavam, he has simplified all the astronomical computations simply by disposing of sin theta and cos theta, the trigonometric functions. A student of astronomy will wonder how it could be done, because it is full of trigonometry, spherical trigonometry. Without spherical trigonometry, you can't imagine mathematical astronomy at all. But it is greatness of Ganesha Daivajna that he substituted the trigonometric function sin x or sin theta by an algebraic approximation, and that approximation is extremely wonderful. And in fact, because most of you have studied physics and mathematics, I may mention it. Today in our modern computations or derivations in applied mathematics, we use the approximation sin theta is approximately theta when theta is small and in radian measure. In fact, this very approximation was used in the derivation of simple pendulum and sin theta, and I don't know whether students were made aware of it. Using that approximation, you could solve the linear differential equation and get it. But in reality, sin theta cannot be that close to theta unless theta is too small. But the question is how small it should be. Well, our physics teacher will think over that, whether they tell their students how small theta, the amplitude of the simple pendulum should be. But anyway, if you tabulate the value of theta and sin theta, where theta is in radians, and you will see that when theta is around 10 degrees or more in degrees, the value of sin theta is not at all that good. So it will be valid only when theta is of the range of 2 degrees, 3 degrees, 4 degrees like that, but not 20 degrees, 30 degrees and so forth. But I am glad and proud to tell you that the approximation, algebraic approximation used by Ganesha Daivajna is wonderful. Even you can have theta as large as you like. You can go even beyond 90 degrees. You may ask, how is it valid if it is 120 degrees, 150 degrees? That is because you can use the formula of allied angles. Sine of 150 degrees is same as sine 30 degrees. So anyway, even up to 90 degrees, the approximation used is very good, correct to 3 decimal places. But does Ganesha Daivajna get credit for this? Credit for simplifying the astronomical procedures definitely goes to Ganesha Daivajna. But that formula, that algebraic approximation itself, the credit goes to first Bhaskara Acharya who was in the 7th century. In his Bhaskara I, he gives this approximation. It is wonderful, it is algebraic, and entire astronomy is simplified. That explains why Ganesha Daivajna's Gralagam is extremely popular among the Panchanga makers. Again, I am proud to tell you and to point out humbly that we from Bangalore have translated Gralagam into English, published by INSA, Indian National Science Academy. We have translated the text to Kannada also, because in North Karnataka, like Dharwad, Belagav, Gadag and such places, and Bijapur, Gralagam is very popular in Panchanga making. Then again, going back to Kerala school, we have the famous mathematician Jeshtadeva. Jeshthadeva's Yukti Bhasha is extremely popular. It is the text which gives you the proofs for most of the mathematical and astronomical results. Usually Indian authors did not have the practice of giving the proofs for mathematical results they gave. Not because they did not know the proofs or derivations, but they had the practical difficulty of writing down all that, because on the palm leaf they had to etch all these results, and to write the mathematical derivation is a lengthy business, much worse to draw curves, circle, etc. And orally it was all knowledge was transmitted, so all these practical difficulties they had. So they didn't have the practice of giving the proofs in their compositions, though definitely they will have taught all these things to their shishyas or students. So this Jeshtadeva does great service to us in the 16th century by giving the proofs of various results. And incidentally, he mentions the sine series, pi by 6 series, tan inverse series, that is what we call the Gregory series for pi by 4. All this Jeshtadeva gives in his Yukti Bhasha. Then we have the last one, Chandrasekhara Samanta. Chandrasekhara Samanta was from Odisha, and his famous text in Sanskrit is Siddhanta Darpana. It's a voluminous text, and there is a mistake here in giving the year. He was in the 19th century, so maybe 1833 he was born in. While typing there is a mistake. So Chandrasekhara Simha, he is also called Patani perhaps, Patani Simha. And today there are our modern scholars in the field from Odisha who have been working on this Siddhanta Darpana of Chandrasekhara Simha. And there was another great astronomer from Odisha by name Shatananda. He is called Shatananda because he divided the major angles into 100 divisions. Normally the practice was to divide into 60 parts. Here he used the metric system. Among Indians he is the first to use that. And in modern expressions, it becomes easier to express a fraction in terms of decimals. Thus, using 100 as the unit is something remarkable of that Shatananda, and one of our friends there in Odisha is working on Shatananda's text. Then Sadratnamala by Shankaravarman is another popular text, and almost among the modern traditional astronomers, we have Venkatesh Ketkar of Maharashtra, but who lived in Bagalkot, which now belongs to Karnataka. His texts are in Sanskrit, Jyotirganitam and Grahaganitam. And there are Panchanga makers throughout India who have been using Ketkar's text. What Ketkar did was to use modern formulae following Newcomb, Leverrier and others, Brown. So their formulae are used but put in Sanskrit in the Siddhantic style, because Panchanga makers would understand only that style and that language. So we have Venkatesh Ketkar. So almost the time is up. and of course I had much to cover, but because my colleagues are also to speak, here are some tabulated results of this number of revolutions of planets and then number of civil days in a Mahayuga. Of course, I can't go into all those details. These are number of revolutions. They all tally with the modern known values. That is something remarkable. So also in the next table, you have the mean daily motion. Even those tally well with modern values, and I have compared in the table the traditional values with modern values. And eclipse computation is something remarkable. And one of my colleagues will be giving you the details of eclipses, so I'm not going into details. With this, I conclude thanking all of you for the patient hearing. I don't know how the presentation came to you because there was a complaint yesterday. There was an audio problem. I don't know if similar thing has happened now. Anyway, if you want any clarification or further references, you are free to contact us, and Professor Ganguly will kindly provide our email addresses to all the participants so that they can popularize the Indian knowledge system among their students by giving them references, and the further work can be turned out. Thank you very much. Thank you, Professor Ganguly, for giving me this opportunity.
Thank you, sir. So now I would request the participants, if they have any direct queries, if they want to ask Professor Balachandran Rao anything directly, there is an opportunity here. You can just ask one or few questions we can take before we move on to the next session.
You mean now?
Yeah, just one or two if somebody wants to ask something.
Okay.
Yeah.
But you are free to send me email.
Yes.
Kindly give them my email
I will give
ID.
them the email address in their one WhatsApp group is there, so they can send you.
Yeah, so that we can work out the details.
Yes.
Here it may be inconvenient to reply because of audio problem and all that.
Okay. No. Today there was no problem at all. Audio was very clear. Your slides were also clear. No problem.
Anyway, thank you for your kindness. And now I will request our colleagues to go ahead.
Yeah. Thank you. So let me thank Professor Balachandran Rao for his talk, and he has come here and delivered us a glimpse of Indian context, astronomy in Indian context, and the contributions which our ancient Indian astronomers have done.